Okay, so we're going to start talking about sound and the ear, the auditory system, and how we perceive sound. We often talk about sound and audition as our sense of hearing. Sometimes we call it audition. Sometimes we call it auditory perception. I want you to stop really and close your eyes and just listen carefully for a little while. Okay, so what do you hear? I don't know how much of my background noises you're hearing, but I have my dehumidifier on and I can hear rain on the roof, but you're going to have different situation because it depends on where you are. If you remember at the very beginning, I said that I was probably going to try to remind you to do this, kind of just stopping and experiencing your senses. And this is really what this next discussion, or the first discussion, is about. And it's focusing on the sense of hearing. I really love my sense of hearing as somebody who started losing her vision before the age of 4 and was legally blind by the time I was 6 years old and got my glasses. Maybe I was 7. I recognize how much I use my auditory localization skills to figure out where birds are, or where people are in the hallway near me, and I can even hear who's coming a little bit, depending on whether or not I know them by their gait, or if it's one of the janitorial workers, they'll have their keys clanging. So our auditory perception tells us a lot about the world, and I think it gets a little bit not appreciated because of what a visual animal we really are, but it is really important. So the sound stimulus, as we started with light and the electromagnetic spectrum, we're now going to be talking about vibrations of molecules. This is a really different kind of stimulus that we get to experience in our perceptual worlds. It is traveling through a physical medium, for example, air, as my voice is now, but it can be through water or through walls. As we know, walls are very dense, so they're blocking a lot of the sound, but some sound gets through. It travels in waves, and so when we're talking about, and it's changes in air pressure, let me go ahead and put that in there. So when we're talking about these vibrations of molecules, what's happening is those molecules are coming together, so causing more air pressure, and then coming apart and causing less air pressure, coming together, causing more air pressure, coming apart. And these these processes of condensation and rarefaction. He shows this in the picture with the with the speaker and the dark gray bands. The increase in air pressure he's showing is condensation. The decrease in air pressure, so those molecules coming farther apart, is rarefaction. And as the speaker is showing this traveling in waves out from the speaker into the world, a point that's important to make is that what's happening with that change in air pressure and the movement of the molecules, that's happening in a particular spot at a particular time. So that gray band that he's pointing to that says condensation, in the next moment in time, that's going to be where there's rarefaction. Okay, so it's traveling out from the sound source, but at the same time, those changes are happening in a particular place. And he compares this very nicely. If that feels like, I don't know that makes a lot of sense, you can look at the picture in B, where if you throw your line into the water or a rock or something into the water, those waves are rippling out from the line or the rock or whatever you threw in the water. But if you had a little toy boat in the water there, it's not going to be pushed out by those waves. It's going to bob up and down because the displacement of the water molecules, that's happening at a particular place right there. That's coming back and forth right there. So hopefully that helps. I really like his pictures there to make that make sense. Sound moves at a fraction of the speed of light. This is why if lightning is far away, we see the lightning and then later hear the thunder. For sound, it moves at 340 meters per second through air, 1,500 meters per second through water, and even faster then through the wall. As we get more dense, it's going to move faster. This always seemed really backwards to me in a lot of ways, but I think over time and teaching this, I've kind of wrapped my head around it. And this is, again, in comparison to the speed of light, which is 300 million meters per second. I'm starting the sound stimulus by showing a pure tone, which is kind of the simplest way to start, just like we did with light, and we had our rainbow colors, and this is the nice perfect sinusoidal waveforms. We're showing this pressure change described by a sine function wave for a pure tone, but we really don't hear these very often. Tuning forks, we can create them electronically. Some authors put flutes in there, but what you can see in the picture in A is it has an amplitude where we have increased pressure, and that amplitude we're going to talk about is giving us loudness. And you can also see it's a waveform, and so from peak to peak we have this measure of wavelength. And what this is showing, what this piece is showing, is one cycle, from one where it's at the no atmospheric pressure change back to no atmospheric pressure change after a condensation and a rarefaction cycle. And then what he's trying to show in B is the condensation, again, those air molecules coming together, and the rarefaction, those air molecules coming apart. So because we have these waveforms that are telling us about the sound stimulus, we're going to see them translate into three aspects of perception. Again, this is just like we did with the electromagnetic spectrum for light. In this case, though, that height of the waveform is telling us amplitude. Again, that was marked very clearly on the previous slide. Amplitude is associated with the perception of loudness. So I'm starting here. The bolded is the physics of the world, and the final word that's bolded is the perception that translates to. Amplitude is measured in sound pressure level, sometimes called SPL, or decibels, or dB. And we're going to talk about decibels very briefly. You don't need to know it, but it's good to know. Sometimes, just so you know this too, they use SPL for decibels. It's just what happens in the field. But this is the size of the pressure changes. And I try to do this. I can't make noise like a sine wave. I can't make a pure tone with my voice. I just can't. Nobody can. But so I'm going to do this, and this is not a pure tone. This does not look like these waveforms at all. It's very, very messy because I'm speaking. But if we look at the very bottom part of the figure with that low amplitude, that would be when I'm whispering. Okay, the middle figure with that sort of moderate amplitude is maybe when I'm talking like normal. And then the large waves that show the high amplitude is when I'm yelling at you. Okay, this is much funner when you're here in class. I think it actually attenuates me a little bit on YouTube. I think I've listened to this before. And like I said, this is extra information, but I think it's important to know so that you do see if what they're doing in a paper is talking about sound pressure level and it looks like it has these huge jumps. Well, it does. So sound pressure level, that relative amplitude, when we're talking about what's just barely audible, we call that 1. As we get into something that's louder, like leaves rustling, maybe 10, quiet residential community 100, but you can tell as we get up to propeller plane at takeoff, we're at 1,000,000, and at jet engine at takeoff, so it's actually at our pain threshold, we're at 10 million. So if we're trying to talk about all of this and we're trying to put it on a figure, so a graph to discuss, that gets to be where if we kept it without exponentially kind of squashing it to some extent, that the jet engine taking off would be up in the air somewhere, like well above our buildings. And so they use a logarithm to get the decibels. So now barely audible is 0, leaves rustling is 20, and we can get the quiet community at 40. And as we get up to way up to the pain threshold, we're still just at 140. Frequency is measured in hertz, and as I was showing the one cycle in the first picture, now we're going to see a number of cycles. So this one is showing almost 3 cycles per second at the bottom, and then still I'm not going to count them out, but like 8, 10 cycles per second, maybe 12 at the top. And this is also showing pure tones, which I can't do with my voice. I also can't create these sounds at these levels with my voice because 3 hertz or cycles per second is below our range of hearing, so I certainly can't produce it. And even 12 or 15 is below our range of hearing, but we're going to pretend. Okay. And so part of this is that we are seeing so many cycles per second. So this is happening through time, and we're measuring that again in hertz. Frequency is associated with pitch. Okay, so again, frequency is the physics of the world, the stimulus, and pitch is our perception of sound that translates into. And I'm going to try to do this with my voice, even though, again, I'm telling you I can't do that. But so at the bottom would be me trying to sound like a big guy. Okay, the middle is maybe me talking as I am, since I'm a female with a relatively deep voice for a female. And then the high one, the one at the top, would be me trying to sound like Mickey Mouse. Okay, so you get that idea that the low pitch versus higher pitch, and that's associated with how many times does this change per second. So now I work backwards from it, but so from the perception to the physics on the other side. But so frequency of the physics gives us our perception of pitch. Amplitude gives us our perception of loudness. I'm going to put in plus frequency, really small there, as we're going to see that our audibility curves and what we can hear, it changes depending on the frequency. So it does really depend on frequency, but mostly we consider loudness as an outcome of amplitude. And then the final one, as we talked about with light, that we had purity or mix, because we're not seeing rainbow reds, we're seeing other like mixes. That's the same thing, right? We don't really usually hear tuning forks or electronically created pure sine waves. What we hear is some mix, and that mix, that specific mix, is going to give us the timbre or the quality of sound of a particular instrument or a particular voice or whatever. It's a good place to go ahead and bring in the notion of tone chroma. This perception that we have when we're moving up a keyboard or we're using a musical instrument and we're hitting the same note or the notes of the same letter. So I think this picture, it's too small for me to see, but I'm pretty sure it's showing you the A's. Not sure if you can see it. As we move up the keyboard, every note that has the letter A has something very much in common. As we start down at, I think it starts with 27.5, moves up to 55, to 110, to 220, to 440, to 880, to 1760, and all the way up to whatever the 3500 one is, way up. But I'm not going to multiply it out because that takes me too long in my head. So, but what you can see, I'm hoping you see, is that 110 is 55 times 2, 220 is 110 times 2. So they share a lot in common because of those, because they are multiples of each other, or they're really that last one times 2. So a complex tone, which is this mix of they're not pure sine waves. It's really made up of multiple pure tones, and pretty much all noises fall into this category. Again, except those very few that I said at the beginning. And I'm going to distinguish here between periodic sounds, where we're seeing those pressure changes repeating. Periodic is this repeating over time. So musical instruments, when I'm holding a particular note, like a C note or an A note, that's going to be a periodic change. A person holding a note when they're singing, same thing. And we also have aperiodic sounds. So they're more complex than periodic sounds, and the typical ones we use as examples are speech and static. static like on the radio or the TV when you don't have it quite tuned in. Like if your radio, you don't have it quite tuned in and it has static, that is constantly changing. It's not a repeating kind of sound. And same with my speech. It is constantly changing unless I'm holding one of my notes. I can't do it very well. So most sounds are complex, and I'm showing here these wrinkles in the waveform. They don't look like perfect sine waves, and again showing amplitude and how that is the height of the waveform wavelength from peak to peak, or from wherever we are at the same place to the same place after going through the condensation and rarefaction through an entire cycle. And that amplitude is based on air pressure, and what you see is these kind of wrinkles in the waveform. And this is showing the wrinkles of the waveform on a piano. I think it's pretty idealized, as you're going to see. And if we had that same note on a violin, those wrinkles, that mixture would be different. So those wrinkles would look different. And so I actually kind of meant to say this on the slide before, but I knew that I repeat some of what Dr. Scott Laird says in his video. He repeats some of what I've already said in his video, but I think it's pretty good. It's pretty helpful to have it repeated. And in his video, he has some really neat animations and three-dimensional animations that show these complex tones. So that's the link on the previous slide under complex tones. So it seems like I'm cutting this really short, but that means the next one will be about 20-25 minutes, which is how I like to do these, because the next thing you're going to do is go watch this Dr. Scott Laird. He is a music teacher at, I think it's, I'm going to say this wrong, North Carolina School of Science and Math, and he shows really nicely these complex tones, these periodic tones, and how they are made up of these various harmonics.